Thank you, everyone. Thank you for joining. Today, Professor Fernanda will give a talk on phase disposition modulation with sorting algorithm for symmetrical cascaded multi-level converters. I thank everybody for joining in, and on behalf of IEEE, PELS Society Bangalore chapter, and also Women in Engineering Bangalore section, I welcome Professor Fernanda. I hope you find it very insightful, and please post your questions in the chat. Please make it as detailed as possible. After the talk, during Q&A section, Professor Fernanda will try to answer. Go ahead, Prof. Please go ahead.
Okay, thank you. Can I? Okay. Thank you very much for your kind introduction, and thank you very much for the invitation to present this webinar today. As I mentioned before, it's always very nice to share a little bit of our work with other people. And I'd like to thank everyone attending this webinar for taking part of your time today to be here with me in this work. And please feel free to ask any questions through the chat, and I'll be very happy to answer them as we finish this presentation. So the paper or the work that I'm going to present today is just a second.
Yep. Yeah, full screen.
Okay.
Oh.
So can you see it the full screen right now?
No, Prof, it is still in that mode. Yes. Now yes.
Okay, that's perfect. So this work is entitled Phase Disposition Modulation with Sorting Algorithm for Symmetrical Cascaded Multilevel Converters. This is a paper that we have published in IEEE last year. The authors are Jean-Michel de Paris, Caio Ruviaro Dantas, Humberto Pinheiro, and myself. So Jean and Caio are PhD students at the Federal University of Santa Maria. And this work was part of the dissertation work of master dissertation work of Jean. And also we have here Professor Humberto Pinheiro, that's a colleague that worked with us at the Federal University of Santa Maria. So as I said, we work at the Federal University of Santa Maria in Brazil. I'm a professor there. So we are located in the very south of Brazil. And we do our research at the Power Electronics and Control Group that we call GEPOC. So this is where this work was performed. So we have here also the authors of this paper, the students Jean and Caio, PhD students, myself and Professor Humberto Pinheiro. So moving on to the technical aspects of the presentation, I will present here a brief introduction of the problem that we are going to work on in this paper, a brief literature review, the proposed sorting algorithm both for normal operation of the converter and when we have fault conditions in the converter power cells. I will present you the experimental setup and implementation of the algorithm in the hardware, and show you some experimental results, and after all, some conclusions. So basically, we are all concerned right now with the problem of the renewable energies and the environmental concerns. So we are relying more and more on cleaner energy sources that are renewable and of course have a minor impact on the environment. And also these renewable sources, they usually allow easier integration into distribution networks and systems. And on this context, we are working with higher and higher power equipments that demands new technology. So in this sense, we can work with semiconductor switches, with new technologies that allow faster switching of frequencies and that allows higher powers, higher voltages and currents. And we can also work with new converter topologies with traditional semiconductor switches, traditional semiconductor devices, that is low voltage and low current semiconductor devices. So in this context of new converter topologies with traditional switches, we have the concept of the multi-level converters. So one of the first topologies that you all are familiar with is the NPC converter, the neutral point clamped converter, that was first presented in 1981. So it's a very good solution for high power or medium power applications, industrial applications. And the original NPC converter allows 3 levels on the phase voltages. So that's why we call them multi-level converters. And we can have multi-level converters with many levels per phase. And this higher number of levels in the converter output voltages, output phase voltages, and of course line-to-line voltages, provides a lower harmonic content on these voltages. So we have a better harmonic performance when we work with multi-level converters. Also, we have reduced stresses on the semiconductor devices. And as a result, we can generate these output voltages with a low distortion and less DVDT stresses on the semiconductor devices. In this context, one of the most widely used and non-multi-level converter nowadays is the cascaded edge bridge topology that we can see here on these slides. So here we have an example of a 3-phase cascaded topology with 3 cells per phase. So we have 7 levels on phase voltages. We have independent DC sources for each one of the converter cells, and we can put more cells in series here in each one of the phases in order to increase the number of the levels on the output voltages. Regarding this DC bus here, we can have, for example, diode rectifiers on the input, and we can also have controlled rectifiers in order to control this DC bus at the input of each one of the cells. So some applications where we can see the cascaded topology are motor drives, active filters, electric vehicles, HVDC, STATCOMs, and interfacing with renewable energy sources, photovoltaic, for example, is becoming very common also for these applications. So, and we also have battery energy storage systems with batteries, where we can find applications with CHB topologies. So it's a very widespread topology, and is used in very different applications. So just to talk a little bit more about the cascaded topology, we have here one of the phases of the inverter. So we have the 3 different cells that comprise this phase. Each one of the cells has its own DC bus, and we have here the output phase voltage that we are calling here VO. So each one of the cells can synthesize 3 different voltage levels, 0, minus VDC, and plus VDC. And we can then put various cells in series in order to have more and more levels per phase. So if we have here N cells, we can have this number of levels in the output voltage. Another very important characteristic of the cascaded converter is the ability to operate when we have faults of the converter power cells. So if, for example, we have a problem in the cell here, we have a problem in the switch, or we have any kind of problem, this cell can be bypassed, and we can reconfigure the control and the modulation of this inverter in order to make it operate even with the loss of this power cell. And it can work with more than 1 faulty cell per phase. It can work with various faulty cells throughout all the converter, based on the fact that we can reconfigure the modulation and the control of this inverter. So it's a very reliable converter, and this is why we see it being used in operations or applications where we must have high reliability rates, such as mining operations and oil drilling and so on and so forth. Another important issue to mention here is that we can have this DC bus voltages here all with the same value, and then we call this topology the symmetrical cascaded converter. Or we can have different values for this DC bus voltages, and then we can call this topology asymmetrical cascaded converter or hybrid cascaded converter. We are going to focus this work here on the symmetrical cascaded converter. So when we work with the asymmetrical, we have some different strategies that we have to apply when it comes to the control and the modulation of the cells. So this is why we are working here with the symmetrical cascaded converter. So here we have just a brief review of some modulation strategies that we can work with multi-level converters. We have basically the space vector-based algorithms that are very well known. So, for example, we have 3D algorithms, 2D algorithms, and so on and so forth. The, let's say, problem with the space vector modulation for multi-level converters is that as we have a very high number of voltage levels, we have a very high number of voltage vectors. So sometimes the modulation strategy can become more complex when it comes to space vector modulation. Of course, there are various works that simplify the space vector modulation for multi-level converters. And on the other hand, we have other strategies such as selective harmonic elimination and PWM. So when it comes to PWM, usually we work with multi-carrier PWM because we have different values for the voltage levels. So we have different levels also for the carriers that are going to be used on the modulation strategy. And we can take as examples the phase shift PWM for the cascaded that we are going to deal with more details in the following slides. And we also have the level shifted PWM. So in phase shifted PWM, we have the carriers phase shifted horizontally. And on the level shifted PWM, the carriers are shifted vertically. So we have this different approach for these two different strategies. Also, another approach that is becoming more popular in the latest years for multi-level converters is model predictive control. That can also be applied with very nice results for multi-level converters. But on this work here, we are going to focus on the level shifted PWM, especially the phase disposition PWM. So basically we have some, we also have here phase disposition, phase opposite disposition, and the APOD, alternate phase disposition modulation. The phase opposition disposition PWM is implemented as you are seeing here on this slide. So the upper carriers or the positive carriers have the same phase, and the negative carriers have opposite phase when compared to the upper carriers. So the number of carriers is related to the number of levels that we have on the output phase voltage. So if we have 5 levels on the output voltage, then we will have 4 carriers to implement the modulation. Other strategy is the alternate phase opposition disposition, where we can see here that the carriers have a phase alternation, 100 degrees offset between 2 consecutive carriers. So you can see that the blue and the red carriers are 180 degrees phase shifted from one another. And we can see here also the red and the green. And the same thing happens for the negative carriers. So this is the alternate phase opposition disposition. We have here the phase shifted PWM, where you can see, as I mentioned before, that the carriers are phase shifted horizontally. So each one of the cells of a given phase has a specific carrier with a specific phase shift, so that we can cancel out the harmonics on the output voltages. And we have the classical phase disposition modulation here on this slide. So here we can see that the classical phase disposition modulation, all the carriers have the same phase. So we don't have any phase disposition, phase alternation among all the carriers that we are going to use on the modulation. The upper carriers and the lower carriers, they all have the same phase. The problem when we use phase disposition in this classical approach is that each one of the converter cells, and consequently the semiconductor devices of the cells, will switch with different frequencies. So each one of the switches will switch or will commutate just when the the reference or modulating voltage passes through its associated carrier. So for example, when we have the carrier, when we have the modulation here in this blue carrier, the switch associated to this carrier will commutate. That's what we are seeing here on the top of this slide. When the modulation signal passes through the red carrier, then we will have that the other switch will take over the PWM, and so on and so forth. And when we add all the signals, then we have the classical multi-level phase voltage of this converter. The problem here is that as we have different number of commutations and switching patterns for each one of the switches, we have different losses, power losses for each one of the switches. And this can be a problem for this converter. So the issue that arises is how we can distribute the pulses for the switches in a way such that they are evenly distributed among all the switches and among all the cells. So many papers have been presented in the literature to deal with this problem in order to distribute in an even way the pulses for the semiconductor devices. So one of the works that have been presented is this one. So we have the reference paper here, in which we have these upper carriers here, that you can see on the upper side of the figure, and we are making we are rotating the carrier. So you can see here that this orange carrier here, it's on this position on this first period, and then it switches position to this other level, and then to the other level, and the same thing happens with the other carriers. So there is a rotation of the carriers for the upper three carriers, the positive carriers, and the same thing happens here for the negative carriers. So this is a relatively simple solution, and ensures adequate output voltages with the levels that are desired, and with a nice and a very good harmonic performance. And it allows power distribution among the cells. But the switches, the individual switches, they still don't have a very good performance. We still have some problems when it comes to the individual switches. We solve the problem for the cells, but we don't solve the problems for the switches. And it also does not address faults in the converter power cells. Another important work here is presented in this other reference here, and we see that the concept of rotating the carriers is extended here, in the sense that the carriers are rotated both for the upper carriers and the lower carriers. So we can see, for example, this blue carrier. In the first period, it's in this level, then it goes down to the other level, and so on and so forth until the end of the period. So in this sense, we also have a simple implementation that also has a very good harmonic performance, and also regarding the levels, the output levels of the voltage. We will have a distribution, an even distribution of power among the cells and among the semiconductor switches. But it also does not address the problems of faults in the power cells, on the inverter power cells. So in this context, we have proposed this new strategy that we call PDS, that is the phase disposition with sorting, in order to obtain a better distribution of the PWM pulses for all the semiconductor switches, and also regarding the power, the balance of the power among the cells. This strategy also allows the use of the algorithm when we have faults on the converter power cells. And the interesting thing here is that we can maintain the good THD and weighted THD indexes for the output voltages, that is a characteristic of the PD modulation, while performing the distribution of the PWM signals and of the losses. That is a natural characteristic of the phase-shifted modulation. So we try to bring the best of both worlds to this implementation. And we will also make some comparisons among our strategy, that is the PDS, the classical phase disposition, phase shift, and both strategies that I have mentioned in the literature review. So if you're interested in more strategies in order to deal with distribution of the pulses among the cells, in the paper that we have published, we have a more detailed literature review regarding this issue. So let's come to the proposed strategy. We are going to work with this three-phase cascaded topology with 3 cells per phase. That is the same one that we have implemented in our lab as our experimental setup that I'm going to show you in the last part of the presentation. So we have the 3 phases, and an important aspect of the modulation that we are going to present is that each one of the phases is treated separately. So we can modulate phase A, phase B, and phase C in a separate way that makes the modulation easier to implement. So first of all, we define this vector that is called V offset, that each one of the entries of this vector, it's a value that reproduces the multiple carriers that we need to implement the modulation strategy. Because as you know, a standard DSP cannot shift the carriers vertically. It can shift the carriers horizontally, like in phase disposition, but we don't have multiple carriers in a DSP in this configuration. So in order to emulate this behavior of the phase disposition modulation in the DSP, we shift the modulating signal. So in order to accomplish this, we have these offset values that are added to the modulating signal in order to emulate the effect of having different vertically shifted carriers. So here, the first 3 positions of this vector are related to the upper switches of the cells, that is S1, S3, and S5 for this configuration with 3 cells that are configured as active high. And S2, S4, and S6 are the last 3 positions of the vector and are configured as active low. So this active high and active low nomenclature comes from the operation of the DSP. So as you may know, we have in the DSP the carrier that counts up to a given value, and we compare a comparator with this carrier in order to generate the pulses for the devices, for the semiconductor devices. So in the active low configuration, what happens is that when we have that the comparator is greater than the carrier, the pulse is on logic level high. And once the comparator achieves the same value of the carrier, the pulse goes to logic level low. This is why it is called active low. And on the other hand, the active high works exactly the opposite. So when we have the comparator higher than the carrier, we have a low logic level for the PWM pulse. And once the comparator and the carrier achieve the same value, the state goes active high. So this switches here, S1, S3, and S5, that are these ones that I am showing here, are configured as active high. And S2, S4, and S6, these 2 switches here, are configured as active low. So as a standard modulation for H-bridge, we have that these lower switches here are complementary to the upper switches. So we just need to actively control the upper switches of each cell. So this is the first important part of the strategy. We have this V offset, this vector with the offsets for the active high switches and active low switches. And we also define here this other vector V and CT that in these entries, in the entries of this vector, we store the number of interrupts that this given switch here did not change its status. So for example, if switch S1 has stayed for 6 interruptions of the carrier without changing its status, the value of this entry will be 6, and so on and so forth. Finally, we also have another vector that is defined, that is the current state of each semiconductor switch. So if this value is 0, we have that the switch is open, and if the value is 1, the switch is closed. So basically, these are the definitions for the modulation. Also, we have here the comparator for each one of the switch, 0 through 5. So comparator 0 is the comparator for a switch S1. Comparator 1 is for switch S3, and so on and so forth. And they are defined as this equation here. So we have the reference voltage that we have here, that is between the maximum value of the carrier. And we subtract from this reference value the value of the offset for that switch that is stored on the vector V offsets. So this subtraction is for that given switch. So let's present some examples in order to see how this modulation works. Let us consider the case in which we have the modulating signal like this, and we sample the modulating signal at the period match of the carrier, that is when the DSP carrier achieves the highest value, that is T peer, we call it T peer here. And we have then that the modulating signal has the value of 5.2 T peer. So the first step of this strategy is, of course, sampling the phase modulating signal for each one of the phases. So this process is doing in parallel for all of the phases, phase A, phase B, and phase C. They are independent from each other. So we have sampled the phase modulating signal. We have achieved this value here. And the second step is to check which V offset entry has the value corresponding to the reference, and save this position. So here we have that the sample voltage is 5.2 T peer. So if you take a look at this value here, this figure here, the modulating signal is somewhere like this. So it is associated to this carrier, that is this upper carrier. And in the V offset vector, we can see that the entry that's associated to this specific interval of the sampled voltage is 5. So we have 5.2 T peer for the modulating voltage, and the entry that has its value associated, this offset value associated with the modulating voltage, is the switch S1. After we do that, we update the vector VPWM with the states of the switches at that given moment. So let us consider that the states of the switches at this interruption is this one. So we have the upper switch is conducting, and the lower switch is, or better saying, the active high switch is conducting, and the active low switches are not conducting. Next step, we analyze the current logic level of the PWM signal. So this switch S1, that is the switch that has the offset value in accordance with the sampled voltage, is conducting. It's on level 1. So we can see it here in this step. As the switch that should be taking over the PWM, that should be conducting, is actually conducting, we will find the highest VNCT value associated with the logic level 1 in this case, and save this position. So the 3 active high switches are with logic level 1, and we can see that switch S3 has stayed longer time period without changing its status. It has stayed for 6 interruptions without changing its status, while switch S1 has just changed its status. We can see here that its entry is equal to 0. So what we do, we reset this entry, we reset this value here from 6 to 0, and we add 1 unit to all the other entries of the VNCT voltage vector, and we have this new voltage vector. After that, we exchange the elements of the V offset vector regarding position 1 and position 2. Position 1 is the switch that should be taking over the PWM, but it has just switched from the previous interruption. And switch S3 stayed for 6 interruptions without switching. So it's time for the switch to take over the PWM. Sorry. So we change these offsets here, these 2 positions. And what happens is that instead of switch 1 take over the PWM, switch S3 will take over the PWM and will commutate. So we have changed this offset. We have changed the offset, and by changing the offsets, it's the same thing as change the reference for that specific switch. And then we force the switch that wasn't commutating for the longer period to take over the PWM. So this is how we perform this sorting algorithm. We find out the switch that stayed for longer time without switching, and then we force this switch to commutate while keeping the other switches without changing its status. Once we have this new V offset, we go back to the start of the interruption routine. So we have another example here for an underflow interruption in which the modulating signal is now at this point. So its value is 4.8 TPIR. So we perform the same steps. We sample the modulating voltage, 4.8 TPIR. We check which V offset entry has the value corresponding to the reference. So now it's this other switch here that is associated to switch S4. Is switch S4 here. Oops, sorry. So we have checked that S4 has the same offset as the sample voltage. We update the value of the VPWM with the switching states. So we have now this switching states here. We see the current logic level of the PWM signal. So switch S4 is conducting, so its switching state is equal to 1. And we have these other 3 switches here that are also conducting, that are also on logic level 1. So when we take a look at these other 3 switches here, S3, S2, and S6, we see that they didn't stay so long without switching. Switch S3 just changed its status, and S4 and S2 and S4. My apologies. S4 and S6 didn't switch for 2 interruptions, but this switch here, that is S2, didn't switch for 4 interruptions. So this is the switch that should take over the PWM right now, with the same logic level as the switch S4. So what we do is that we reset this value here and add 1 value to the other ones and exchange these 2 positions for the offsets. So instead of switch S4 take over the PWM, S2 is taking over the PWM, and it's changing its status in this interruption. And then once we have this new value of the V offset, we go back to the start and sample the reference again, and so on and so forth. So let's come to some results to demonstrate the operation of this modulation strategy. So here we have the reference voltages or reference signals for each one of the phases, reference A, B, and C. They are escalonated between 0 and 600, because we are considering that the carrier of the DSP is between 0 and 100. And the shape of these reference voltages comes from this paper that I have published some time ago that was related to my master thesis. And it's a generalized carrier-based strategy for cascaded converters operating under fault conditions. So basically what we do in this strategy, we find the linear region for the converter, for the operation of the converter, that is given by this curve, is the blue curve and the green curve. And we choose a common mode voltage that belongs to this linear region, and we add to the sinusoidal references for each one of the phases, resulting in this reference voltage. So by using this, we can make sure that the converter will not overmodulate. It will be always working inside the linear region. And it also will allow us to work with fault conditions on the power cells. We are going to go back to this strategy on the next slides. But considering this normal condition with modulation index equal to 1, we have here the conventional phase disposition modulation. So for each one of the cells, we have these voltages. And we have the voltages for the cells of phase A for our proposed PDS modulation. So we can see here that we have an even distribution of the pulses among the 3 power cells of the converter. The same thing applies to the other phases, phase A, phase B, and phase C. So we can see the improvement between these two results. So in this other slide here, we make some comparisons among the classical PD modulation for this converter with modulation index equal to 1 and sampling frequency of 3 kilohertz. These are the results for reference R1 that I have mentioned on the literature review. So we can see that R1 distribute the pulses among the switches, but they are switching at a high frequency here, and then they spend some time without switching. So the pulses are distributed among the switches, but they are not evenly distributed among the period of the fundamental frequency. Here we have the results for the R2 strategy that are also presented on the literature review. And these are the results for our proposed strategy. So we can see that they have similar results, but for the R2 strategy, there are some intervals here in which the switches commutate with a higher frequency, such as like here and like here. And we don't see this behavior in the proposed PDS strategy. Moving on to the comparisons, here we have the output line-to-line voltages for the PDS and PD strategies. So we have the waveforms on the time domain and also the spectra of these voltages. So what happens is that the output line-to-line voltages for the PD and PDS modulation are exactly the same. So this proves that we are able to achieve very good output line-to-line voltages with a very good harmonic performance, while also performing the distribution of the pulses among all the semiconductor devices. So we have a very good harmonic performance that is the characteristic of the PD modulation, while also achieving even power distribution and even pulses distribution among the cells and the switches. That's the characteristic of the phase shift modulation. So for this case, the amplitude of the fundamental components of the output voltages was supposed to be 600 volts, and we can see that the synthesized output voltages are very close to desired values. For comparison, we have here the results for strategy R1 that are also very good, and for strategy R2 that are also very good. We have also some comparisons here between the PD modulation and the PDS modulation, in which we count the number of commutations for the switches during 1 second. So we can see here that switches S1 and S6 that are the switches that take over the PWM. The PWM here and here, they obviously have a larger number of commutations than these other switches that are in the middle. So we can see here in this slide exactly this behavior. Those upper and lower switches, they switch much more than the intermediate switches. And for the proposed PDS modulation, we have that all the switches, all the 6 switches, have a very similar number of commutations throughout 1 second. Another comparison that we have is the actual number of commutations over one period of the fundamental of the fundamental of the modulating voltage for modulating index equal to 1. So we can see here that the PD and the PDS strategies have a similar number of commutations, the total number of commutations, even though for the PDS, the upper and lower switches commutate more than the intermediate switches. And here we have a very similar result for all the switches for the PDS. And here, strategies R1 and R2, we can see that they have a slightly different value for the number of commutations for the switches, and they have a higher total number of commutations when compared to the proposed strategy. We also present here some comparisons regarding the THD and weighted THD for the output line-to-line voltages, for the 4 phase disposition strategies, and also for the phase shift. So for the phase shift, we have implemented this strategy with a frequency of the carrier divided by 6, so that we can have the first harmonics at the same position, and we have a fair comparison among all the strategies. So we can see, as expected, that the phase shift PWM has higher values for the harmonic content for THD and WTHD. And the proposed PDS strategy has values very similar to the PD, R1, and R2 strategies, and slightly better performance than the R1 and R2 strategies. Also, here we have a table with the power losses per leg of each one of the H bridges, so each one of the cells. So, for example, for the PD, we have these total losses. And for the PDS, we have very similar results for the total losses. But take a look here, we have even distribution of the power losses among the cells, while for the PD strategy, we don't have this even distribution. The strategies R1 and R2, even though they result in quite distributed losses, they also result in higher losses for the semiconductor devices. And now we are going to move on to the dynamic adaptation of the offset vectors when we have fault conditions on the power cells. So what happens here on the operation of the converter with faulty cells is that we must bypass the faulty cells and reconfigure the modulation in order for the converter. So in this strategy, bypassed cells are also taken off of the modulation strategy by assigning to it a very large value for their offsets. So this very large value makes the cells actually make the algorithm blind to these cells. So it's just as they do not exist. So in this case, we have a fault on the cell A1. We have a fault on one cell of phase 1. And we can see here that we have assigned a very large value to the offset of the switches that are associated to cell A1. So this cell is taken out of operation. If we have two faults, like one fault on cell A2 and one fault on cell A3, two faulty cells on phase A, we assign a very high value to the offsets of the switches of these respective cells. So this strategy can work with any number of faulty cells in the converter. We don't restrict the number of faulty cells. It can operate with any fault condition. So, for example, if cell A1 is bypassed, as we can see here in this figure, we assign that large values for the offsets, and we also force here that the number of commutations in this vector VNCT is smaller than 0. So this will make sure that we are not considering these switches on the analysis of the modulation implementation. So we have here results for this case. We have here, for example, two faults, actually 3 faults on the converter, a fault on cell A2 and 2 faults on phase B, on cells B2 and B3, and a modulation index equal to 0.5. So we can see here in phase B that cells B2 and B3 are bypassed. They are not synthesizing voltage. And we have this PWM for cell B2. However, when we use our proposed strategy, we can see that we are able to evenly distribute the pulses among the remaining cells, the remaining switches, the operating switches. Although we have higher number of commutations when compared to the operation without faults. This happens because these switches here try to compensate the absence of the PWM signals of the other switches. So this is why they switch at higher frequency when compared to the normal operation condition. But we can see the even distribution of the pulses. We have here some results for this same fault condition. The fundamental amplitudes for the output voltages that were supposed to be 300 volts, and they are very close to the desired value. We have the THD and the weighted THD for the phase shift modulation for this configuration of fault, the PD and the PDS. So again, we have a very good harmonic performance for the PDS strategy, while also distributing the pulses among the operating semiconductor devices. Here we have a graph that shows the maximum modulation index and the respective THD and WTHD for different fault conditions. So if we don't have faults on the inverter, we can achieve up to modulation index equal to 1. And as we lose some power cells, then we are not able to achieve this maximum modulation index equal to 1. The modulation index is a little bit lower for fault conditions. So fault type 1 is when we have just one faulty cell on the converter, or better saying, one faulty cell actually on the converter. Fault type 2 is when we have two faulty cells in different phases. For example, one faulty cell in phase A and one in phase C. And fault type 3 is when we have one faulty cell in one phase and two on the other. For example, one in phase A and two on phase B. But we can have also different conditions. We can have more faulty cells, like for example, all faulty cells in one phase and another phase with one or two faulty cells. So we can have many different configurations for faults here. So now we come to the experimental setup. We have here the three-phase CHB converter. Each one of the cells is composed by a back-to-back single-phase H-bridge. We have a figure of the experimental setup here, the complete converter with the 9 power cells and the central controller. And here is the figure of one of the power cells with the local controller. I will skip this one and also this, and move forward to the experimental results. So here we have the output phase voltages without faults for M equal to 0.6, and also the line-to-line voltage. So we can see the very good performance of the strategy. And here we can see the pulses for the switches of phase A. We can see the very good distribution of the pulses for phase A. Now we have a fault condition for phase A and phase C. We can see here the phase voltages and the line-to-line voltages that are balanced. And we have here the pulses distribution for the operating switches. These are for phase A, and here for phase C. Very similar results for both phases. And a final experimental result for other fault condition where we have one fault on phase A and two faults on phase B. So here we can see the phase voltages and the line-to-line voltages, and also the PWM pulses for the active switches. Also a brief comparison of the execution time. We can see that we have a very similar execution time for the 4 strategies that were implemented. And we move on to the conclusions. So the main reason for using this phase disposition with sorting is to accomplish both even power distribution and even pulses distribution for all the semiconductor devices of the cascaded converter, while also achieving the very good harmonic performance for this output voltages. So the harmonic performance is a characteristic of the PD modulation that is maintained in our strategy. And the even distribution of the power and of the pulses is a natural characteristic of the phase shift modulation that we also maintain in our strategy. So this sums up what I have just mentioned. And thank you very much for your time. And if you have any questions, please feel free to ask, that I am able to. I'll try to answer them as much as possible. So thank you very much for your attention.
Thank you very much, Professor. Very good talk, very detailed talk. Thank you very much. It was good to see that you built 100 kilowatt power converter in the lab. Very good to know. We'll take a couple of questions. Nachiketa has asked, generation of isolated DC sources might have a large impact on the cost and complexity of the system. Is the cascaded H-bridge topology viable, including the mechanism to generate a large number of isolated DC sources?
Yes, that's a very interesting question, because this can be a problem for cascaded converters. So let me just go back to the experimental setup. I moved a little bit fast in the end because I noticed that we were running out of time. So
no problem. Yeah.
Our topology, the individual DC bus voltages, they are accomplished by means of this active front end here. So we have the DC bus and you have a totally controlled rectifier. And although we have more switches to control, and I didn't enter into the control of the rectifier because it's not the purpose of this paper, but these rectifiers, they are connected to the input transformer. And as we have active control of the switches, we don't need those huge and costly input transformers that we usually have on cascaded converters. So if you have diode rectification, you need to have those different phase angles for the input transformers in order to diminish the harmonic content of the input currents and so on and so forth. So this input transformer is very simple and it makes its cost very low and it's easy to build because it's just a one-to-one transformer. Each phase has 3 secondaries, but they are standard secondaries. They don't have any different windings or different angles and so on and so forth. So all these issues regarding the rectification are dealt with the control of the rectifier. So we have low distortion input currents because of the active rectification and of the simple three-phase transformer here.
But the transformer will be pretty big, right?
Sorry?
The transformer size will be pretty big, right?
Yes, the transformer is big. The transformer is big, yes, because of high power.
Okay. Shaili, okay. Nachiket, does that answer your question? Are you here? Okay. Shaili has a question. Shaili, if you're there, you can unmute yourself and go ahead. Okay. Okay, the question is, what kind of faults, I think you answered that, what kind of faults in the converter of power cells are mitigated? So, yeah, I think you answered that in the presentation. Yeah, if you could go to slide 24.
24, just a second here.
Yeah. Others, please post your questions here.
Do you want me to answer?
Yeah, I just wanted to know about the interruptions. When you say the interruptions, what do you mean exactly? Number of interruptions do not change the state. So I'm guessing you have S1 to S6. So what do you mean by number of interruptions here? I just wanted to know.
Okay, when you have a standard PWM, the switches will switch, let's say so, for almost all the interruptions. But when you have the phase disposition, sometimes a given switch will stay for a very long time without changing its status. So, this very long time is associated to the underflows and period mass of the carriers, the interruptions of the PWM carrier in which you calculate your control action and your modulation strategy. So we count the number of interruptions of the carrier that each one of that has occurred during the time, and if that given switch changed its status on that interruption or not. So this vector stores the number of DSP interruptions that the switch did not change its status. So this is
basically,
how please go ahead.
Please go. Yeah. What I was saying was an interruption refers to change of state, right? From 0 to 1 or 1 to 0. That is known as one interruption. Okay.
Yes.
Thank you, Prof. Yeah, I had one more question. Yeah, the order of switches. Can you go to the circuit diagram where you had the PC and DSP, or just the order of switches?
Which slide? Sorry.
I think it was in the end. I think it was in the end where you had the PC grid and the number of switches. Yeah. So did you face any? Next, where you had the diagram? Yeah.
Okay.
Yeah, where you had the circle 57, I believe.
Which one? Sorry.
57, I think. Slide 57. Slide 57.
That's.
Oh, where you had the circuit diagram, just the circuit diagram, the grid, PC, DSP, yeah, before this,
This
or
one.
after this, maybe. Yes. Thank you,
Okay.
thank you. So did you, no, just before that. Yeah. Sorry. Yes, this is 59. So did you have any shoot through or any possibility of shoot through at all when you were trying to implement it?
Can you repeat, please? What problem?
Shoot through. Did you have any shoot through phases, shoot through instances during implementation? Did you have a case?
Short circuit. I had a problem here. I didn't. The audio was put for a little while. I didn't listen.
Okay, sorry. Yeah, all I wanted to know was two switches in a single leg. How did you make sure that they weren't on at the same time? That's all.
Oh, you have the dead times of the switches here.
Okay.
They have the dead time, so they don't conduct at the same time.
Good. Thank you, Prof. Yeah, and you mentioned two frequencies. You had 3 kilohertz and 15 kilohertz. What are these two frequencies? The switching frequency is 15 kilohertz.
You mean this is light? Or
okay. Okay. The switching frequency was what?
we have in the experiment implementation this configuration here. The DSP, the central DSP, but we have the local DSP inverters working at 3 kilohertz. This is the central controller here that performs the control of the whole. But the inverters of each one of the cells, they are switching at 3 kilohertz.
Okay.
This higher switching for the DSP, for the local, for the central DSP, is just to perform the control of the overall inverter.
Okay. Sorry. Okay. DSP. Okay. Good, Prof. And in the results, if you go to slide 56, 56. Yeah, 56.
56. Okay. 56.
Yeah.
This one?
Others, please post. Yeah. Here, what is the difference between the two faults? And by faults, you mean they are not at all conducting, right? They are turned off. A2, B2, and B3 are off. Is that a fault?
Yes. On this case, we have one faulty cell on phase A and two faulty cells on phase B. That's B2 and B3. And we have the modulation index equal to 0.5. Because once you have faulty cells, you must lower the modulation index. Otherwise, the converter will saturate. It will not be able to synthesize the voltage. So here we are showing that if we use this the phase disposition approach with this fault condition, we have that the remaining switches on phase B, they have this high switching frequency because they try to compensate the PWM of the other ones that are not switching, that are bypassed. But they have this natural characteristic of the PD that they spend some time without switching. So we have this we don't have pulses. And if we apply our strategy, even though we have these other switches bypassed, we can see that we can evenly distribute the pulses throughout all the fundamental cycle. So even though it still has a higher switching frequency because we don't have PWM here on the other cells, but we are able to distribute the pulses in the switches.
Okay, okay. And does this even distribution have any impact on the power loss?
Yes, they do. So if we come back to the, let me see if I have these results here. No, for the normal operation, we are presenting some, just let me find the slide in just a second.
Yeah, sure. Others, please put the questions in the chat. Yeah.
Yeah, so this
Yes.
is for normal operation, but we can see, even though the same thing, you can see that for the PD, we don't have the even distribution of the pulses, and we have higher losses for the switches. And when we compare to our strategy, both strategies have this a similar distribution of the losses for the switches. But we can see that all the switches in the PDS, our strategy, they have very similar losses. If we take a look on these other strategies, R1 and R2, they also have some distribution, as you can see here. For example, this is R2, but it switch more on some instance, and R1, they distribute the pulses just on these intervals here, and you can see that on this other you don't have switching. So when we see the losses of this strategy, if you go back to this table, you can see that they have a higher losses when compared to our strategy. And just to remind that all strategies were implemented with the same switching frequency. So yes, we have higher losses for the other strategies, and our strategy is able to bring the losses a little bit lower than the other strategies.
Understood. Very good, Prof. Very good. Before we question, which software did you use for simulation when you were trying to simulate?
Sorry, the audio was also a little bit. Can you repeat?
Which software did you use during simulation phase of the work? Software. Very good. Okay. Adresh, can you please go ahead, unmute yourself and go ahead.
Hello, ma'am.
Yeah. Yes. Please ask your question.
Hello. My question is that during the fault, suppose in one phase one cell is not working, then must be the output voltage will be imbalanced. So do you have any modulation scheme to make it balance, or because it will affect in the load? What will you do when it will be imbalanced?
What? Sorry, I didn't listen to the last part of the question.
It's also in the chat. You can just read it. I'll just read it out. Okay. During any cell fault, the output voltage will be imbalanced. Output voltage is imbalanced. So do you have any method to mitigate this output voltage imbalance? That is the question.
Okay.
Is it the question?
When we have fault conditions, we will have imbalances on the phases, right? We have imbalances on the phases because we have different number of cells on the phase. But what really matters when concerns to the load is the output line-to-line voltages. And the output line-to-line voltages, they are balanced. So if you see here, this is a condition with one fault in cell A and two faults on the phase B. You see that the output phase voltages, they are imbalanced, but the output line-to-line voltages, they are very balanced. They have the very same amplitudes for their fundamental components. And this is achieved by means of the paper that I have mentioned before, that I have published in 2012. Yes. Here we have the algorithm that was developed on this paper. I'll just skip these slides for a while, and I'm going to show you this. So we can calculate the linear region for the inverted operation without overmodulation, and we can find this common mode voltage here that is going to be added to the voltage reference that would be sinusoidal. So adding this common mode voltage here to the balanced sinusoidal references, we have this other reference here for phases A, B, and C. So for phase A, we have a faulty cell, and we have a faulty cell in phase B. So you can see that the reference voltages for the cells are very different from one another. But when it comes to the output line-to-line voltages, these different or unbalanced phase voltages, they result in balanced output voltages, output line-to-line voltages. So yes, the phases are unbalanced, the phases have different amplitudes, but what concerns the load are the output line-to-line voltages, and the output line-to-line voltages are balanced. So if you want more details on this implementation, you can take a look on the paper that we have published, or you can send me an email and we can discuss it with more details.
Good, good. Adrish, does that answer your question?
Yes, ma'am.
Adrish?
Yes.
Yeah,
Yes, ma'am.
Please introduce yourself to professor so that she knows what is your background, what are you doing.
Ma'am, I am doing my PhD. I'm working on induction motor drive, and you have mentioned that model predictive control in your initial site. I'm working on that model predictive control.
Very good, very good.
Very interesting.
Very good.
One more question, ma'am, I have. You have in your slide there is a local DSP and the central DSP. So how do you synchronize in both the DSP?
This is a nice question also. And maybe I can show here. So what happens is that we have the central DSP. You can see here the central DSP that synchronizes all the cells. So when we have these carriers here, you can see that the central DSP is working at 12 kilohertz, and it sends a package through fiber optic communication. It's a serial communication protocol that we have developed. And this package of data makes the synchronization of the local controllers, the local cells, with the central controller. So you have here this interruption of the DSP carrier. You have a communication delay, of course. It's a very small communication delay. But then you synchronize the local DSP inverter that is working with 3 kilohertz to the central DSP carrier, both for the underflow of this carrier and the period match of the carrier. Here, the rectifier, the active rectification, is working at 6 kilohertz just to have a better harmonic content on the input current, that is the connection of the rectifier to the grid. But then the synchronization of the local cells and the central DSP is done through this communication protocol that sends data packages from the central DSP to the local DSPs, and these data packages, they perform the synchronization of the cells.
So did you have any follow-up, Adrish, or did that answer your question? I think, okay, the synchronization is done
yes,
by...
ma'am. Yes, ma'am.
We have this slide that I also passed a little bit fast. We have the central DSP here, and we have the faces that we have developed. So this communication is done by fiber optics, and the central DSP sends the package to all the cells. So we have a serial communication to phase A, one to phase B, and one to phase C. And these packages that are sent to the cells, they contain a byte that is responsible for the synchronization. The cell, once the cell receives this data package, it interprets the package as a signal to synchronize with the central DSP. So this is how we perform a synchronization. And also the cells send back an information to the central DSP just to make sure that they are working well. So if we have any problems with the cell sends back a package that says, okay, I'm having some trouble, do something. And this is how we have this back-to-back communication. The central inverter, or better say central controller, and the local controllers.
Good, good. Very good, Prof. I had one last final question. What is the startup sequence for your hardware setup? Is there a startup sequence that you follow when you, because yes, it's 100 kilowatt?
So we have some slides here, also extra slides, sorry.
Very interesting work, Prof. I have not seen 100 kilowatt. In lab we used to.
This is basically a controller. This is a control for the rectifier, and we have here this waveform will show better what I want to do. But first we give some free charge to the DC bus without controlling the rectifiers. We just connect.
We are yet to see the slide. Which maybe are you showing any other slide? We are seeing a slide. Is this the slide you wanted to show? Or do you have one? Okay. Pre-charging.
These are the voltages of the capacitors for the DC bus voltages of phase A. So first of all, we give a pre-charge on the capacitors without controlling the rectifier, just a pre-charge connected to the grid and pre-charge to a given value. And then we keep the inverter open. We don't control the inverter, and we start controlling the rectifiers. So we have a special mode of operation in the central DSP that only controls the rectifier in order for the DC bus voltage to be on the desired value. Once we achieve the desired value, each one of the cells measures this value and sends back to the central DSP a package that says, okay, my voltage is controlled to the desired value. And once we have all the cells controlled and with the right value for the DC bus voltages, only then the central DSP will change the operation of the inverter, and we will start to perform the modulation of the inverter itself.
Okay. Good. Very good, Prof. Yeah, because I also face some difficulties usually in startup sequence for my converter as well. Okay, Prof. Thank you very much. Thank you, everyone. Thank you very much, Prof. It was really very good presentation. Very well explained. And thank you for your time for explaining the paper and answering all the questions. So on behalf of IEEE IES PELS Society Bangalore chapter as well as Women in Engineering Bangalore chapter, I thank you very much for the presentation.
Thank you very much. And if you have any further questions, please feel free to send by email, and then I'll answer them all. So thank you for the invitation again, and have a good night there.
Yeah. Good morning to you. Thank you, Prof. Thank you.
Thank you. Bye-bye.